Hi, everybody. Welcome to the podcast on Everyday Metallurgy. This episode is about biomining. Could you imagine small minions, archaea, or bacteria that has been around on the Earth for 2 to 3 billion years, that they could harvest our raw material in the minings? That is what Professor Barrie Johnson will share with you in this episode. It is really, really marvelous what is possible with biomining. It is not that slow that I thought, but follow the episode and learn from Barry. Perfect. Hi, Barry. Welcome to the podcast of Everyday Metallurgy.
Well, thanks very much. It's good to be a part of this.
And thank you for accepting my invitation. You're an expert in a field that, for me, is pretty new, biomining. Uh, can you give a short background of who you are and how long do you have been in this field?
Okay, my current position is Professor Emeritus at Bangor University. Now, this is a smallish university based in the northwest corner of Wales, between the mountains and quite close to the sea. And I've done most of my active research here in Bangor, time spent in the US Department of Energy. I'm also a research professor part-time at Coventry University in England, and also I hold a position of a research associate at the Natural History Museum that maybe many of your visitors will be familiar with. It's a primary location in the centre of London, and basically they're establishing the area of research which I've given up now, actively at least, and I'm acting as an advisor in establishing it in the NHM. So that's quite an exciting time.
Hmm.
I've also held honorary positions, honorary chairs in a university in China, Central South University, and Exeter University in the UK.
Okay. Pretty busy around in the world.
Yeah, it's been interesting because, working in mining and the mining sector,
Hmm.
I've been privileged to work with virtually all of the major players from time to time. Probably most interaction with Rio Tinto over the years.
Hmm.
I continue to advise on a major Rio Tinto project with the NHM.
Yeah.
But mining isn't big anymore in the UK as in many European countries. So uh,
Hmm.
you have to take an international perspective, which
Yeah.
goes into Europe. There's a lot of
Hmm.
interest in some countries in Europe with mining and post-mining activities.
Hmm.
Interested in post-mining in the UK. But then it takes you to various corners of the globe, South America, South Africa,
Hmm.
Australia,
Yeah.
and into Asia. So it's very much an international area.
Yeah. Yeah, the European mining industry might soon wake up again. The act with critical raw material is kind of making incentives for introducing mining again in Europe. So maybe there's some activities that could use your expertise.
Well, there certainly is biomining activity been going on in Finland for the last 20 years, and
Okay.
also there's interest in countries like Poland, which have major mining activities. So yeah, there are opportunities.
Hmm.
And maybe we talk about later as well in reprocessing waste materials. And there's a lot of waste in
Yeah.
Europe because we have done mining in
Yeah.
large scale in the past.
Hmm. Yeah. Thank you. Let's take a jump back to the fundamentals. What is this biomining? How was it invented? Can you say something about it's microbes that are working for you, but where are these microbes found and how do they work?
Okay, I'll take you back to where they were first found because it's an interesting story. They weren't
Yeah.
found in a metal mine as such. Some researchers working in West Virginia in the United States back in the
Mm,
1940s were looking at a waste stream draining a coal mine, as it happens. Now, maybe many people are familiar with the fact that streams from coal mine and coal mine refuse sometimes have this reddish orangey tinge,
mm,
and that's due to the presence of iron. And what these researchers found was that there was a bacterium in this water that was changing the ion chemistry from one form, iron 2, to iron 3. Iron 3 is the color of rust.
Mm-hmm.
And when they looked at it and isolated it, they saw it grow in sulfur as well, but that it only grew in acidic liquids, which this stream was. Many streams
Yeah.
draining mines are acidic, sometimes extremely acidic.
Yeah.
So they isolated it, and when they studied it, they had the hunch that maybe this organism could break down fool's gold, iron pyrite.
Mm-hmm.
So they did the tests, and they found it could, because there's iron and sulfur in fool's gold.
Yeah.
And then they took the leap of saying, well, if it can do fool's gold, maybe it can break down other sulfides, such as copper sulfides.
Mm-hmm.
Experiments proved successful. And not long after that, in the early 1960s, the first application, a very crude application of biomining, was carried out at two mines in the US, one in Utah and
Mm-hmm.
the other in New Mexico. They're both owned by the same corporation called Kennecott, which has disappeared now. And that was done basically to extract and win copper from what they call run-of-mine ore. This is the material which contains some of the metal, but it's so low grade, it's not worth processing for making
Mm-hmm.
concentrates or whatever.
Yeah.
And so basically, they did a very crude application of irrigating the dumps that they constructed, and copper was coming out in the stream, the other end, and that was recovered by a very old technology. I call it cementation, where they threw scrap
Mm-hmm.
iron into the stream. Copper came out by electrochemistry,
Yeah.
and that gave them extra revenue of copper. So
Mm.
that's the first documentation. But
Yeah.
if you look back in history, it's fascinating because you can find some evidence in Roman writings and certainly in the Middle Ages in Europe and possibly in China as well, that these sorts of activities were being carried out, this cementation technique. So they were
Mm.
using the biological route without knowing about bacteria. Of course, bacteria weren't known at all then.
Yeah.
So that's where it got its roots. And since then,
Mm.
the engineering has evolved and become far more sophisticated.
Mm. Yeah. These bacteria, I thought that these sulfide-eating bacteria, they were found in near undersea volcanoes.
Yeah, you do find some of them in the deep sea hydrothermal vents or whatever.
Mm.
Because of the pH buffering of seawater, they tend to be slightly different sulfur mineral eating microorganisms in the main.
Mm-hmm.
Um, but these organisms, you find them, for example, I did a lot of my work when I was researching in the US in Yellowstone, and there was a lot of these similar organisms, a lot of them like in hotter temperatures,
Yeah.
in geothermal areas. You get them in Iceland,
Mm.
in New Zealand and whatever. But in cooler areas, if you go to mine dumps, a lot of the work we did was in the Mediterranean, Iberian Peninsula, and
Mm.
you find them everywhere there, also in cooler climes, including Scandinavia
Okay.
and UK. So yeah, they're pretty ubiquitous. And of course, bacteria have generally got a bad press because a very, very small percentage are associated with health problems and whatever. But
Mm.
these are totally innocuous. They live in sulfuric acid. They really can't live outside of a very acidic environment. Not
Yeah.
even in our stomachs, which is hydrochloric acid. They don't like that
Mm.
acid. They only like sulfuric acid.
Okay. Yeah.
So they're pretty specialized.
So it's not hazardous to people at all.
Absolutely no, but
Mm.
it's always the case with dealing with microorganisms that
Mm.
you do take care. But no, there's absolutely in my long career, uh,
Mm.
none. I've never had a problem. None of my team have ever had a problem with these organisms. They have a problem with us, maybe more than the other way around.
Yeah. Yeah. Um, there are two ways they work. One is called bio-leach, another one is called bio-oxidation. Can you describe how that works? Those two ways of refining with microbes.
Yeah, it's basically one and the same process. It's just what happens to the metals. In bio-leaching, we're looking at metals which are solubilized in acidic solutions. So The main one that's biomined by bio-leaching is copper. Always has been, was the first and still remains the biggest of them. There are other metals such as nickel and zinc and the like, which are solubilized. So they come into solution as a result of the breakdown of the minerals that these organisms are breaking down, the bacteria. A lovely word for them, by the way, is lithotrophs, which is rock eaters. I like that term because basically
Yeah.
the minerals dissolving in front of you.
Mm-hmm.
You feed the bacteria with them. So yeah, so metals go into solution. So that's bio-leaching.
Mm-hmm.
Then they are recovered by various techniques. Solvent extraction, electrowinning is a very widely used technique now. In the case of bio-oxidation, you're looking at metals, and they normally noble metals such as gold that are not solubilized in acid. And the goal of the microorganisms there is to facilitate their extraction. So if you can imagine very, very fine grains of gold, that is native gold, and they're surrounded by minerals such as pyrite, fool's gold again, so gold in fool's gold, but
Yeah.
also, more importantly, another mineral called arsenopyrite, which is iron, arsenic, and sulfur in a mineral. And these organisms will degrade and solubilize those metals, so they strip the surrounding minerals, and now the gold is exposed. And so the gold, the bugs have done their bits. That's the end of the biological process. And the next stage is to extract the gold from the modified ore. These things like cyanide, people are looking at thiosulfate because of the toxicity of cyanide and whatever. So that's bio-oxidation. It's the oxidation of the minerals, but not the solubilization of the metal.
Yeah. Is it only sulfides that work this way?
It's only sulfides that have been bioprocessed in full scale, but other metals can be either enhanced or recovered using alternative technologies. So one of the technologies we worked on for the last 15 years, we initiated it with a company in Australia. At the time, it was BHP Billiton. That's been done and has become a focus of major research in various laboratories and has pilot scales. And basically what we're doing there is to use very much the same microorganisms as in conventional biomining, but to change the engineering, to change the configuration. Well, if you do that, and these bacteria are really very, very clever because they normally use oxygen. Like you and I, in fact, I call them like plants because they have very minimal requirements. So plants need solar energy. These use chemical energy. They need nutrients, nitrogen, phosphorus. They need water, and they need oxygen. And then they break down the minerals, the sulfide minerals. But if you take away the oxygen, some of them can do something else quite special, and that is instead of using oxygen, they use iron. And the form of iron they use is, again, the form they use in rust. So if you look at an oxidized material, and the chief material we were looking at here was laterite. Now, lateritic ores are in various parts of the world, mostly in the tropics. You get them in Australia, through Philippines, in parts of South America again, in Brazil. And they are important reserves of nickel and to a lesser extent cobalt. So what we were able to do there is to show that just by changing the engineering and using very much the same microorganisms, you could get the iron 3 minerals to be degraded. When you did that, out popped the nickel and the cobalt. So you solubilized them. So it was a bio-leaching, and we call it biomining in reverse gear, because it's using oxygen, you're consuming oxygen. It's just going backwards. So it's using something which discovered by groups in Netherlands and ourselves, but at the same time in the 1990s, that this iron could be used as we call it an electron acceptor. So yeah, it does go beyond there, but that is not as developed as the conventional biomining.
No. So in fact, you could say this is the opposite way of microbial induced corrosion.
Absolutely, you're taking what would you think of as corroded, but it's fully oxidized material, quite the opposite to a sulfide ore. And you just go backwards. Instead of oxidizing the sulfide ore, you reduce the iron ore. But the only downside of that, these microorganisms, as I said, they get their energy from sulfide minerals. The energy is already locked up there. But if you give them an iron ore, you have to give them an energy source because there's no energy to be had in reducing it. So normally what we did was to give them elemental sulfur, which is very plentiful and very cost effective, and it makes sulfuric acid as well. So, there are ways of doing it, but the technologies now are well established. Like I say, had been two independent tests that I know of in Brazil, one carried out by us, another by a group in Germany, looking at this technology. And I'm very convinced it will become full scale soon.
So you just feed it with sulfur like that?
Yeah. Oh no, you just mix the ore with some sulfur, elemental sulfur.
Yeah.
You can do it in on block, or you can do it in two separate reactors. The configurations are still to be worked out to be optimal, but yeah, there are various ways of doing it.
Yeah. Yeah, but I had a discussion with a friend last day about this subject, and we talked about microbes have been around for 2 billion years. Uh, they have optimized what they do compared to us. We have only been around for a million years, something like that. So we are pretty ineffective in the way we work compared to microbes. Is that also the feeling you have?
Oh, that's a very, very astute observation, and it's important to remember that these organisms have been able to colonize every part of the planet that's habitable, where basically you have water in its liquid phase, which sometimes exceeds 100 degrees centigrade if you've got pressure.
Yeah.
Microorganisms, bacteria, and their cousins called archaea, they inhabit all sorts of niches which we are not able to inhabit, and of course they can do all sorts of tricks which we can't. A lot of them just are like us, they break down organic carbon, but these are very, very, very different. They probably are some of the most ancient life forms we have on the planet, and this is why some of them have been thought of as candidate organisms for extraterrestrial environments as well, where you haven't got a lot of solar energy. You do have chemical energy in the
Yeah.
forms of minerals and whatever. So
Hmm.
yeah, they're pretty special.
Yeah. Yeah. And has been developing for a billion years more than we have. So we
Absolutely.
have to take care.
And they're not doing this for our benefit. We harness them to do biomining, but they work on their own time scales and whatever. So yeah, they're in it for themselves as we're in it for ourselves as well. So we have
Yeah.
to compromise sometimes.
Yeah. Uh, yeah. That leads me to this. They they work in their own time. How long time are we talking about? Because when I've seen mining activities, it's typically something like 30 cubic meter per minute they handle in the machineries. Uh, what is the dimensions you talk about when we go biomining? What
Dimensions are big.
volume and time?
The dimensions are big. So the most primitive application, dump leaching, you get dumps of low grade ore and run of mill rocks and whatever, hundreds of meters high, and these are just irrigated. The time scale for processing them can be anything from about 2 to 5 years. So you have to be patient in that. So these were,
Mm,
like I said, the very first applications, and it really didn't matter because the mine owners were happy to get a little bit of extra revenue from the copper that was being recovered from what was otherwise waste.
mm,
Now, a refinement on this approach is called heap leaching, where the rocks are ground and graded, put on impermeable bases, sometimes inoculated and fed. And importantly, very importantly, to speed up the process, they're aerated because the bacteria require both oxygen.
mm.
They also require carbon dioxide. Like I said, they're like green plants.
Uh-huh.
So they fix CO2. Those
Mm,
sort of operations generally can be about up to about a year. Again, the scale of heaps can be very, very large, covering many hectares of land, as they are in Terrafame in Finland and in large tracts. The biggest example in the world is in Escondida mine in Chile, where you have very large areas, and not only large areas, but after one area is worked out, they put another layer on top, and another layer on top of that, so about 7 or 8 layers. They look like ziggurats at the end of the day. These
Okay.
very old Babylonian structures,
Yeah.
but they're huge, and obviously at the end of the day they are dismantled and then put back to where they were. But at that stage, the metals will have been recovered. The other option, which needs to be mentioned, is
Mm.
mostly done for gold, has been done for cobalt, where the concentrate material is processed in large tanks,
Hmm.
metal tanks, stainless steel
Yeah.
tanks, 1,000 cubic meters time. They're again, these are stirred, nutrients are fed into the bacteria.
Mm.
And this sort of process takes about 3 days, 3 to 5 days. So very
Wow.
much cutting down. So the key to speeding things up is changing the engineering
Mm.
rather than the bacteria. The bacteria can go faster if you give them better conditions.
Mm.
But that's about as fast as you can go. And so it doesn't compare to Timescale as competing technologies, pyrometallurgy and high pressure leaching and the like. So it is a slower process,
Yeah.
but there are benefits.
Mm. Yeah. And when we compare with pyrometallurgy, there are a lot of activities now trying to make pyrometallurgy green. Um, is this one of the methods to make the standard extraction greener?
There are greener credentials for bioprocessing than for pyrometallurgy in all sorts of ways. Obviously, CO2 and energy input. One of the main benefits is actually to do with arsenic, because when you roast an ore and it contains arsenic, then it
Mm.
goes up in the smelter in the flue gases, and then eventually comes down into the countryside.
Yeah.
Uh, this is obviously not a good thing. In hydrometallurgy and biomining, it's just one aspect of hydrometallurgy. The arsenic is kept in liquid phase.
Mm.
When you keep it in liquid phase, at the end of the day, you can take it out of the liquid phase and immobilize it again into a solid new mineral phase. It's normally a mineral called scorodite, which is an iron arsenate, and thereby secure it. So there are advantages there. One of the problems is, though, when you're competing with an established technology, then it's difficult to get inroads at the start. So if a
Mm.
mining company has invested millions of euros or dollars in a new smelter, they need to use it.
Yeah.
They don't want to be diverted into a different way of doing things.
Mm.
They want to just stick to that. But if new opportunities arise, shipping ore bodies and concentrates around the world, is becoming less feasible, then biomining has an opportunity, as it has in other areas, as maybe we'll get onto
Mm.
a little later.
Yeah. Uh, but so the main advantage going green is that you can concentrate it, and you don't have to ship non-valid materials around.
Yeah,
Is that what I'm saying?
you can by processing, for example, in Chile, where they still use bioprocessing to extract lots and lots of copper. Basically, they do solvent extraction, electrowinning to make metallic copper there. Now, most of the ore from the Chilean mines is actually exported to other countries to be smelted. So, it's
Mhm.
it's a toss-up which is economically more viable. And sometimes when you put the environmental argument on top, of course, then it becomes clear that alternative technologies to pyrometallurgy are probably superior. But
Mm.
it's what is established and what is the ongoing um, process that the companies use is sometimes hard to break into.
Mm.
There are other areas where biomining can, or Because bioprocessing technologies can be applied where, conventional mining cannot.
Yeah. I had talked to Per Jonsson from LKAB, the Swedish company harvesting iron ore in the northern part of Sweden. They have found large amount of rare earth elements in their long tail. I asked him if they had any activities on going biomining on that, but they did not. Are you familiar with any activities enabling biomining on rare earth elements?
Yeah, there's one project that I'm currently involved with, which is to do with resource recovery from waste streams, and that's maybe an area we should address a little later, where rare earths are present in the water body. But the more direct area which we investigated with a company in Brazil about 10 years ago was specifically for rare earths. And what they had was a problem where rare earths, which don't occur as sulfide minerals, so you're
Mm,
not getting bacteria to attack these directly,
yeah,
but the rare earth minerals, mostly phosphates, were held in iron-rich bodies. So if you can imagine grains of these minerals, and they
yeah.
were surrounded by iron-3 minerals,
Hmm.
like hematite and goethite and whatever.
Yeah.
And what they asked us to do was to see whether we could help facilitate the liberation of these rare earths. And so what we
Mm,
did was reverse process. We got the bacteria to degrade the iron minerals, to
yeah.
solubilize them. That then exposed the rare earths and solubilized them to some extent, because we were doing this in acid, and
Mm,
that worked. There is something to be done there if you have a peculiar situation where rare earths are to be found mostly in these phases associated with iron-3 minerals.
mm. Yeah. I think they are like that in the northern part of Europe, because they are harvesting iron ore and it's quite pure, and they had areas where it's they left it some years ago because there was a too high level of phosphorus. So it might be the phosphorus that is connected in the mineral to the rare earth, as you also said. So it could be a way of increasing the yield factor.
Yeah, I'm familiar with laboratory-based research, and it hasn't gone beyond there, where
Mm,
people have used the fact that these bacteria, I said they can grow in sulfur as well. When they grow in sulfur, they make sulfuric acid. So you can use the sulfuric acid, which is produced biologically, to solubilize the phosphate minerals that rare earths are associated with.
mm,
And sometimes, and this one I've less confidence about, but there are some microorganisms that produce organic acids as byproducts. Now, these are very good at degrading rare earth phosphates. The problem is the cost involved, and the other problems with using. These are different sorts of microorganisms to the conventional biomining type,
okay.
but they have been shown that they can. So who
Mm,
knows what the future will hold? At the moment, the economics are totally wrong, I think.
mm. I'm just interrupting because Barry's talking a lot about different minerals, and to give you some insight in those minerals, he's talking about iron sulfide, and iron sulfide, the bacteria can dissolve that by eating the sulfur, and when it's in rare earth material, rare earth often comes in bastanite. Bastanite is a carbonate fluoride, so the bacteria cannot attack that. Another mineral is monazite. That's what you see behind me. Monazite is a phosphate with rare earth elements mainly. So what it does is that the bacteria can dissolve the iron sulfate, typically in a pyrite mineral, and then it leaves what has not been dissolved behind it. So thereby you are able to upgrade it and make it in high concentration. So that is one of the ways you can use biomining to up concentrate from, if you have a mine with 0.5% of the material you want to get out, then you can up concentrate it using biomining and dissolve what you don't want to handle, and then maybe get up to 5-10% in your concentrate. Pretty nice. Yeah. Uh, when I first found this subject, I thought it must be gene modified microbes. Are you aware if there are any modifying the genes to build another extraction level into the microbes?
Yeah, it's funny. When I first worked in the United States Department of Energy in Idaho, there was a group there, a pioneering group, which were doing just that. They were trying to manipulate one of the key biomining microorganisms. It wasn't easy because, like I said, they live in sulfuric acid, so you've got all sorts of problems to overcome. They had some success. Since then, it's been shown in various labs that you can manipulate them.
Hmm.
My argument has always been that's not such a good idea. Main reason being that it's very hard, in fact impossible, to contain these microorganisms in a biomining operation. So some will get out into the environment.
Yeah.
So if you got genetically modified microorganisms going out into the environment, you have problems. Not that I don't think they cause problems at all. I don't think they survive very long. But it's all sorts of legislation against things like this. And secondly, I've argued that if you want to use a slightly better organism, because maybe your raw body has got some peculiarity, maybe an extra amount of chloride, which is a bit of a problem with some of these organisms, just go out and find one, because there are so many niches, natural environments where these organisms live, and you probably will find one then. And of course, if it's a natural environment, it's a natural organism, so
Yeah.
you don't have to do a GM. So yeah, there's a case for putting all sorts of additional genes into some of these organisms to boost them. Um, my experience is that when you do that, you put them into a natural environment like a biomining operation, they die out because they can't compete with the indigenous microorganisms.
Okay. Yeah. Um, yeah. So there are not only one or two types. There are millions of biofamilies, but it's just about to find them.
So I'd say at the moment there are about 30, maybe get up to about 40 different species
Mm,
of organisms that can be used in biomining. Having said that, in most operations, you're looking at about 5 or 6 which crop up much of the time. The only difference becomes if you try to do biomining, and has been demonstrated at a high temperature, say 80 degrees, which is about as high as you can go,
mhm.
then the organisms become different types. They're not bacteria anymore. They're cousins called archaea. But in
Okay.
most operations which are operated, let's see, typical temperature between 35, 45, something like that, degrees, and these become naturally very warm heaps because it's an exothermic reaction, the breakdown of these minerals,
Mm,
then yeah, you get the same organisms. I call them the likely culprits. When in the 2010, we did a lot of work with mining companies looking at what was there because it was known at the time, and we were able to predict at the end what they'd find because it was so reproducible.
mm. So how do you move them around? Do you start with a bare field without any microbes, and then you carry a liter of your concentrated, or how do you start up a biomine?
Well, when we did work in what is now Terrafame, was Talvivaara in the past in Finland in the 2004, 2008 on a European project, we looked around, and what we found is that the whole area was so teeming with these organisms, you didn't have to inoculate. So you just set up the engineering and basically let the indigenous microorganisms go, because I mean, these ore bodies are exposed on the surface, and when they're exposed, the bacteria know they're exposed. It's just, you know, having a pile of food and on your for the birds, and the birds come and feed on them. They know where it is, and they colonize.
Yeah.
Now, in other parts, in other situations, say these stirred tank operations for gold,
Mm.
the company which does this may establish a new operation in a very different part of the world. And what they do there is to take a cubic meter or so of the um, colonized material from an old operation, which you know have got the
Mm-hmm.
right bacteria there. They
Yeah.
take it to the new one and begin to build up the population in the new operation. So they do inoculate.
Mm.
And in other parts of the world as well, even in heaps, inoculation is used, though often the inoculation is using indigenous microorganisms with their minimum requirements to give them a little bit of agricultural fertilizer, and they're very happy, a bit of nitrogen, phosphorus, and potassium,
Mm.
and they're away. They have minimal requirements.
Yeah. It was like the same way my mother made bread when I was a kid. She had a small bucket of yeast,
Yeah,
and you had to feed it every week. But you could pass it on, and you could share it with friends who want to make the same bread recipe.
it's exactly the same. Yeah.
Yeah.
In-
So we're back in the kitchen. uh, Then, if we look a little forward in applications for biomining, we've already talked a little about we have a lot of waste, and in Europe there are a lot of activities in what we call urban mining. Can we harvest from our waste? That I know there are a lot of activities in trying to do that, but some of them you have to go far back in the loop, almost back to the mineral again. Uh, is biomining playing an active role in urban mining?
There's a lot of research. I'm not sure if it's got to any pilot scale operation yet, but a lot of research in using the same microorganisms we use in processing minerals for e-wastes and metal waste in general. So electronic waste can be
Mm.
solubilized,
Yeah.
bio-leached, if you like, by the
Hmm.
same microorganisms. Because one of the characteristics of the biomining microorganisms is that they tend to be very resistant to metals, such as copper, zinc, and whatever that you
Mm.
might find. So you get organisms to generate acid, they break down the metals go into solution, and then once they're in solution, you can win them, you pull them out individually. So
Yeah.
there's a lot of activity going on
Mm.
in using these microorganisms for e-wastes in particular,
Yeah.
batteries and whatever. So
Yeah.
that there
And
is
and
potential.
and these guys.
Absolutely. Yeah.
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 I saw that. I think it was there are 34 different elements, metallic elements in a phone. And how do you separate it when it's not very big, only few grams of each element. So it's very costly if you should separate it mechanically.
Yeah. No, you're dead right, and the separation has to be done eventually. But what the microorganisms do, they don't separate. They'll just leach virtually everything they can leach,
Yeah.
uh, solubilize from something like your ground up mobile phone.
Mm.
Then you have a stream, a downstream that needs to be separated, and there are separate technologies which are available for that, for taking out, say, the cobalt. I even get the gold at the end. The gold has come in solution, of course,
Yeah.
but the other metals can be one. So it's basically that's more of a complex recovery process, because in most biomining operations, you're looking at one principal
Mm.
metal. Not all in the terrafame operation. It's it's zinc and copper and other metals. Nickel is the main one. So there is separation there, but it's much more complicated when you have a real
Mm.
cocktail of metals
Yeah.
in e-waste.
Mm. Yeah. Do you know how many tons per year that are refined by biomining compared to traditional mining technology?
I haven't got the tonnage, but in terms of percentage,
Yeah.
it's still a niche technology. I hold my hands up there because in terms of winning of metals, it's about has been between 10 and 15% of copper. I'd say it's probably about 5% now. I think it's gone down a lot
Okay.
because the technique has receded a little bit in Chile.
Mm.
About 1%, maybe 1 to 2% of gold. Small percentages up to about 5% of other base metals. Uranium has been bio-leached in the past as well from old mines, but you're
Okay.
talking about very small amounts still
Yeah.
from these incubations. Whereas my my feeling is that in the future we are going to use bioprocessing more extensively for mine waste, solid mine waste and liquid mine waste, where they really are superior in many ways. And there are examples of this
Mm.
already in full-scale operations where biomining can be used, where maybe you've only got about 1% of the metal in the waste, which is not so
Hmm.
bad when you consider there are mines operating in Sweden where there's taken out copper, which is present at 0.2, 0.3% in the ore body. So
Oh.
percent in a waste is pretty good.
Yeah.
Um, and I think as we've already touched on, there are lots of waste materials in Europe, rest of the world, where there are metals, resources, which weren't thought of at the time as being important, including the
Mm.
rare earth.
Yeah.
There was a lovely example, which I use all the time in Uganda, where there was a huge mine waste, which from copper mining, which was environmental hazard, so something needed to be done. But what they found when they looked at it is that it contained a lot of cobalt, about 1% cobalt. And
Hmm.
cobalt is much more valuable now, of course, than
Yeah.
copper at the time.
Yeah.
So they bioprocessed that in tanks, they recovered the cobalt, it paid for
Hmm.
the cleanup operation, and it was a win-win all round. And that was a good example of biomining full scale.
Yeah.
It only ended when the whole of the waste was used up and nothing, nowhere else to go there.
Mm. Yeah, and it's a good idea to build up cobalt extraction other places than Congo.
Totally. Yeah,
Yeah.
indeed. Yeah. I mean, there are, we were looking 5 years ago or so at mines where cobalt was present and associated with arsenic.
Mm.
We did some demonstration technologies there, again, using the idea that keeping the arsenic in solution is a good idea. You can extract the cobalt, it's easily one cobalt in solution and can be secured safely. So
Mm.
cobalt, it's an interesting one because cobalt was only used as a pigment for hundreds of years, and then suddenly you have this explosion in the demand for cobalt in batteries and the like.
Mm. Yeah. Uh, Barry, the last subject I would like to jump into is I have read that some are trying or foreseeing that biomining can also be used in space explorations. So going to Mars and extracting minerals on Mars using biomining. What is your view on that?
I think it's interesting. Just a little sideback. Many years back, there's a TV program BBC makes called The Sky at Night, and they're looking at the possibility of life on Mars, and then we knew the red planet was full of iron oxides,
Hmm.
and this is associated with often in our own planet with places like Rio Tinto, where you have organisms like the type I work on, Rio Tinto in Spain now, not Rio Tinto, the company.
Mm.
They did an interview and they showed the sort of organisms we had. And it's clear that the biomining organisms could survive in somewhere like Mars as long as they had what they require, and that's water. Okay,
Yeah, liquid water.
liquid water, liquid
Yeah.
water. The organisms we have on our planet, they work down to about 5 degrees, but Mars is a lot cooler than that. So they need to
Hmm.
have a reasonable temperature.
Yeah.
Well, and nutrients, they probably would get away with the nutrient demand. I don't know much about the Martian regolith. They need CO2,
Yeah.
and
There's
they
plenty of
need
CO2 there.
plenty of CO2, but they need oxygen as well. So yeah, as long as this is conventional biomining. So yeah, I think that it would not be out of the question, shall we say, to use them because
Mhm.
they are using chemical energy at the
Mm.
end of the day. But conditions are not universally ideal, shall we say, on Mars.
Mhm. Yeah. Yeah. So it's not first step to run for that.
No, no, but some people have done experiments in which they've recreated extraterrestrial conditions and looked at survival, if nothing else, of these organisms, and they do survive. And
Yeah.
if they survive, then you can get them to become active. And obviously, if you do that, then you have a possibility of getting metals, if there's a colony established in Mars, getting the metals that they require. But it's a long way to go. I think we'll be
Mm.
taking things there for a long, long time first.
Yeah. Um, so how do you see the future of biomining? Where are we in 10 years here on our planet?
Okay, I think reprocessing solid waste is going to be a big business for biomining.
Hmm.
Also, wastewater is coming from mines, and I mentioned that the first organisms came from a coal mine waste stream. But if you look
Yeah.
at metal mines, and there are waste streams coming from them, and these contain metals in solution. I call them natural biomines because basically they're doing exactly what we want in a constructed biomine,
Hmm.
but they're doing it because the microorganisms are doing their own thing. So they're producing soluble metals that comes out in the stream. Uh, the main difference is that the concentration of these metals is smaller than in a constructed biomine.
Mm.
But we can use microorganisms to recover them selectively. And this is one of the biggest projects that we are working on at the moment. I'm just consulting on it with a major mining company. It's Rio Tinto again.
Yeah.
Selectively pulling out metals. The waste stream we're looking at contains more than enough copper to pay for the operation. At the
Mm.
moment, it's just going into streams and rivers, so we can
Mm.
recover them. Rare earths, zinc as well in these waste
Yeah.
streams. Another area which we've not touched upon is what we call deep in situ biomining. So if you think of it, we've been extracting mining metals for millennia. We've now extracted more in the last 30 years than in the whole of prehistory.
Mm.
And we're running out of deposits on the surface which are accessible.
Mm.
If we go deeper into the crust, then there are still large reserves of metals which we can access. The problem is they're kilometer, maybe 2 kilometers below the surface.
Yeah.
So getting down to these areas and mining conventionally is not easy. You can't do it by open cast operations, obviously. But what we could do, and again, a big European project in the late 2014, 2018, I think it was, we looked at something which was not originally our own idea, but others have thought of it as well. And that is basically drilling down to these ore bodies, injecting the microorganisms to do what they need to do, and
Hmm.
then pump up to the surface the liquids which contain the metals in solution. And this in situ biomining in the deep lithosphere is something which has considerable potential, I think, for getting metals out. Again, there are legislations, and you have to be very, very careful with
Mm.
contamination. But at the end of the day, human populations are going to require metals, and to get them out in ways which are more environmentally benign than we've done in the past, I think should be a priority. And this is one of the ways of doing it, deep
Mm.
in situ biomining.
Yeah. So it's you drill a hole and you make a pit, and then the bioactivity make this pit larger and larger.
Well, what you do is actually drill two parallel holes. All right, one is to inject, and one is to extract. And once
Hmm.
you've got them in place, you do a bit of I don't like using this word, but fracturing, basically opening up the ore body. So you make channels. A little bit of in the project we had a pilot scale operation in Poland. We were using controlled explosions, but you could use other things, hydrofracturing or whatever, to make little channels because these will open up along weak bodies where the minerals are, and then injecting under pressure liquids with the bacteria or our idea was actually to have the bacteria on the surface just to get them to make the liquids, inject them. Once the liquids are in place, they solubilize the minerals that you want to solubilize, and then the second well is used to pump up the what's called the pregnant liquor, the liquor with the metals, to the surface where it is captured, extracted, and then the water is recirculated. So the idea that we generated was to have a biological operation on the surface, making the liquor, which, because at the end of the day, 95% of what we're doing is chemistry. We're just getting the bugs to make the chemistry we want. To get the chemistry right, inject acidic, oxidized, iron-rich, iron-3 rich liquors, solubilize the minerals, and to pump to the surface and recover using established technologies. So this is something which, again, I know all of the major mining companies are looking at because they see it as a great possibility for the future.
Yeah.
In Europe, it's more tricky because of density of populations. But once the technology is established, it would cut down, for example, the size of a mining operation, the size something like of a football field, because the amount of land surface you need is tiny compared to what is.
Yeah, of course. Yeah. And what is the time in that operation? Are we talking years or are we talking days again?
Well, I think that would be a question of days. Yeah, it would be a faster operation for the circulation of the liquor from the surface back up to the surface, injected deep subsurface and then back to the surface. Obviously, you have to protect against unwanted migration, particularly as you're injecting down. So if you're injecting to, say, 1.5 kilometers, you don't want this liquid to seep a few hundred meters from the surface. But that's not a problem. It's how the downpipes are constructed, and that's easy. It's the liquids are easy.
Yeah. There are tubes that can work for that to avoid leak.
Yeah.
Fantastic. Thank you, Barrie. I don't have more questions. I am fully loaded with new input from a world that I didn't know of just a few months ago. So thank you very much.
Well, it's been a great pleasure to talk to you, and hopefully this will encourage more interest in the subject because it is a fascinating and I think developing area.
Yeah, and if people want to learn more about it, would you give some advices where they could find out?
Yeah, I mean, there are lots of general reviews. If you go online and look at word search for biomining, I co-edited a book called, I just hold it up to the camera, on the side of it, Biomining Technologies. Don't know if you can see that. That basically has contributions from industry and the leading scientists throughout the world, going from the past, what's happening now, into the future. It looks at different countries, what's happening in China, what's happening in Europe, America, whatever. So it's a good comprehensive recent account. But yeah, go online, do a biomining search, or contact me if no, I like to point you in the right direction, send some reviews, and take it from there. But there are organizations in Europe, as well as the rest of the world, who are involved in active biomining research.
Fantastic. Thank you very much.
Thank you. Well,
yeah.
Good day.
Yeah, you too.
Back.
Bye.
Bye.
Thank you very much for following this episode. I'll be very happy if you'll share or give it a like. But if you are curious to learn more, you're also very welcome to post comments in this video for Barrie. I'll pass the question forward to him and have him answer if I'm not able to answer myself. I am really looking forward to seeing you again, because I have more episodes coming up with really interesting content. So see you soon. Bye.